I'm going to talk to you about the AST, the standard module of Python. A little bit of backstory. I discovered it here, like not here, but in Florence 2 years ago during a lunch break. I was just speaking with some guru programmer. He told me, like, yeah, you should try it for one of my personal projects. And I tried it. It was a really, really good library. It helped me a lot. And sometimes it even turns out to be useful at work. So it's, I mean, I'm using it since 2 years in several different projects scattered because, I mean, every time you have to do with Python code, this can help you. This helps me. So a little bit of the agenda. I would like to motivate, talk about like why it could make sense to talk about the AST standard library. Then I would like to talk about the tree, its nodes. I think that it is boring to mention the nodes, but they are important because in the second part, when we talk about walking the tree, when we talk about the AST and how we traverse it, the nodes are very important for the API, so knowing them can help you. Then putting some demo, showing some code running, and then maybe some conclusions. So, okay. Let's imagine that you have to process some Python code. Okay, today, no, you do not have to connect to a DB, you do not have to open a CSV. No, the raw input today for you, you wake up and no, you have to process Python code. It's a string, and so what can you do? You can use regular expressions. It makes a lot of sense. Some people may laugh because, I don't know if you laugh because of pair, love the guy. Regular expressions, however, they are pretty much a good choice. And I mean, I advocate for them, they are good. Or you can start to write your own stuff. You can start to say, okay, read lines. If def is in line, okay, I have a function, that stuff. Yeah, you can write your own stuff. Or you can give your coding input to an LLM, and the LLM will do stuff for you. All of these approaches, they are actually good. I'm not here to advocate against any of them, but actually you are managing a string. So you are still in the string manipulation phase. It's as if you were to open a CSV, and okay, you open the string and you start to split by comma, but now you're managing a string. Nobody does that. We just import pandas, we import polars, and we read the CSV. We use a parser for this. And then we have a data structure, we have the data frame. So what if we have to process Python code and we just have a data structure that represents our Python code? We just have these, well, at the end of the day, it's the abstract syntax tree. You just have this abstract syntax tree, you explore it, you play with that, but you don't have to manipulate a string. Just, I mean, AST did that for you. As a final round of motivation, there are a lot of very cool people that do very cool stuff with AST. For example, on the PsychoPG3 blog, there is a blog post in which they say that they don't write the synchronous code for PsychoPG3. They write the asynchronous code, and then there is a snippet powered by AST. They use AST to write automatically the synchronous code. Also, I mean, I don't know if you heard of, I spoke with Antonio Cuni, the guy who was talking about SPY yesterday, and he uses AST. So behind a lot of very, very cool projects, this library is there. So, I mean, it's cool, it's useful. And at this point, you may be wondering, okay, but how do you obtain this abstract syntax tree? That's the cool thing. It's super easy. AST is in the standard, because Python, it needs the abstract syntax tree to run, so it's there. But it gets exposed. There is this AST library, which is basically, how to say, a kind of wrapper around already the internal CPython stuff that allows you to access it directly through Python. So you can just import AST, say ast.parse, feed it in, input your code, and bang, you're there. You have the abstract syntax tree. From here, you can play and do whatever you want. In this case, we want to have the abstract syntax tree of hello world, and we use dump. Dump is like JSON dumps, you get the string representation of the abstract syntax tree. And so in this case, what do we have? A module, because, we fed it in input a module with just one code line. It will have a body, which will have an expression, which is a call, because we are calling a function. And the call, well, it has a name, which is print. It could be also something like, you have a dictionary of strings, of dictionary of functions, and you access it. But in this case, it's just a name, it's print. And you are feeding in it a constant, because we basically hard wrote in the code, okay, hello world. And that is our abstract syntax tree. It's a module with a call, with a name, and the argument is a constant. And so what you may be, I don't know if you already have, any of you ever, I forgot about the thing, just for me to get an idea. How many of us have ever, ever played with the abstract syntax tree library in Python? Okay, some of us. In other languages? Okay, a good portion of us. If you are like me, 2 years ago, it was the first time I came across an abstract syntax tree, okay, there are nodes of different types. And actually, the whole idea is that you can kind of think, okay, for every grammatical expression inside Python, there is a corresponding AST node type. And this gives rise to a thing that, I mean, I wouldn't say that polymorphic is the right way to describe this tree, but the abstract syntax tree is different from maybe like the common binary tree that you have in your brain, because, I mean, a binary tree, every node is of the same type. Every node has a left child and a right child, and they are just all the same. No, in abstract syntax tree, you will have a module. The module has a body, and inside the body, there are all of the other statements. You have an assignment. The assignments will have some targets, some values, and the whole idea is that when you have to play with that, the types of nodes are different, and also their own parent-child relationships, they are different. They depend on the specific grammar construct that you are encountering. So there are nodes of many different types, many different types. Most of them, you come to them with intuition. I mean, you can just like, okay, you can understand what they are, but they have some things in common inside the library. So most of the nodes, they possess their coordinates inside the code. They have a line number, an end line number, a column offset, so that you can basically say, okay, this node was located in this portion of the code if you maintain your original string. And also at the same time, like function, classes, loops, like every time you kind of like have to have a tab indentation, you unlock a body attribute, which will be then the list of the sub-statements of your node. So let's say that you have a function definition. The function will have a body. In this case, the body will contain a pair of assignments, a for loop, and then a return. Inside the for loop, there is going to be another body, which is its own body with its own, in this case, a couple of augmented assignments. Just one thing that I would have liked to tell myself like 2 years ago, there are not just bodies. So for example, a try-catch has handlers, and like maybe the for loop will have an or else. In this case, the or else will be just an empty list or none, but body, you will encounter it in many places, but maybe, okay, now you come up to an if may have an else, and the else will be represented as an attribute. So when you want to iterate over them, just be careful. Be careful because there are some other attributes rather than just body. And then, okay, I will show you some example of nodes. I guess that this is boring, but as I said, when we encounter visitors and transformers, like the APIs of the AST kind of like use the node names to allow you to get, to call callbacks and whatever. So at the end of the day, they will turn out to be useful, again, later. So for example, you define a class, and every time you define a class in your code, in the abstract syntax tree, there will be a corresponding ast.classDef node. You define a function, okay, this is an ast.functionDef. A return statement, I mean, return is an element of the Python grammar. There is a corresponding ast.return node type inside the ast. Print is a call, so you're calling something, you're invoking a call, okay, this is a node of type call. There are nodes for the basic data structures, so you're defining a list. There will be a node for the native list. There are also nodes for the data structures comprehensions. And, well, it's kind of like mostly intuitive, I hope, up to this point. But I would like to tell you some subtleties because I discovered them in not the bad way, but I mean, I would have liked somebody to tell me those things in advance. First thing that you can basically, like, how to say, kind of like expect. If you forget about the existence of import lib and other evil stuff, like you can maybe like import things in Python into different ways. Import JSON, from JSON import loads. Okay. These things map to 2 different types of nodes. That is important because let's say that at a certain point you're like, oh, okay, I'm analyzing this code. What is it importing? When you want to do that, you want to keep track of 2 different types of nodes. Functions, everything asynchronous has its own kind of like corresponding counterpart. So let's say that you're interested in say, oh, I want to see all the functions inside my code. If you just take a look at nodes of type ast.functionDef, you are going to miss all of the node types, all of your asynchronous functions. And the most thing ever, those are assignments. So you may think, okay, in this case, I'm just assigning, if I want to keep track of all the assignments inside my function, okay, I just need to take a look at ast.assign because it is an assignment. No. Annotations, they map to a completely different type of node, which is ast.unassign, which makes also a lot of sense from the grammar standpoint because you can say foo equal bar equal 1, and in such case, both foo and bar gets targeted by the assignment. In an annotated assignment, you cannot do that. Also, if you take a look at the attributes of these 2 classes, because after all, we were just talking about classes, and they will have attributes, they are different. For us, for ast.assign, you have a list. For ast.unassign, you just have one specific target, which is the specific variable that you are performing an assignment on. Also, one thing that I never got to try to play, but I was taking a look, there is an AST.try star in the official documentation. So I warn you, if you ever are interested in tracking down your try statements, just be careful at try star. One cool thing, there are type annotations. As far as I know, the abstract syntax tree treats type annotations the same way that Python does. It basically ignores them, but it reports them to you. So if you want to say, okay, just a function def, what is its returns type? It has a returns R attribute, which is the actual type annotation. And they are scattered also, the AST, that annotated annotation, will have all of the, will basically allow you to find again all of the type hinting that you are putting inside your code. It's there, you have it with you. Arrived at this point. I hope that that thing did not bore you too much. We arrived at like the maybe like funnier part when we can like traverse our tree. And in doing it is like super easy because AST comes equipped with a lot of support functionalities rather than only the actual syntax tree. You get to have a lot of things that allow you to play with it. And if you want to iterate all over all the descendants of either your abstract syntax tree or maybe just a subnode, you just need to invoke est.walk. It's a function, you give it a node, and then it will iterate through all of the children. It does so in no particular order, so it is unordered. And to give you an idea of how it works, what it does, I try to prepare this kind of like little game. I hope this is accessible and you can basically distinguish the different colors. But this is basically just a stupid Fibonacci that I wrote. And in the higher part, there is not the code. There is just an indication that tells you like the node number, the line when it happens, and actually the class, the type class. What I'm basically doing is taking the output of ast.walk and store it in a list under the hood, which basically means that we are actually taking a look, we will take a look at the ordered nodes that come in an unordered way out of walk. Basically, walk starts from the shallowest nodes in your abstract syntax tree. The root is the ast.module, and basically descends up into the down into the deepest ones. So in this case, like the first node that you actually meet in your module is when you walk it, is the actual function def Fibonacci. Next node will be starting from the shallowest, the next if inside your code in the module, which is the if name equal main. Going further, we will encounter like the first child of first node that we saw of the first node of the like first level of depth over tree. So we will basically encounter the first if comprised with its else. And I mean, like, I like to play with it, go on and go further. And but I would like to stop at this point and showcase you that like walk with also like take all of the like say intermediate expressions inside your code. That is like the cool thing about the abstract syntax tree. It doesn't just take a look at your code lines. It takes a look at all of the expressions. And up to this point, since we are basically just running through the output of walk, we encounter, like, for example, in this case, a Boolean operation, that it is like the 7th node that we actually have, but the index started from 0, so it was the 8th. And we have a Boolean operation, which will have two children, I = 0, I = 1. And maybe we are asking ourselves, okay, but these specific comparison nodes, when are we going to see them? The answer that I always like to say is, as you understood, walk will be unordered, so we will first have to go through all of the other children of the parent of that poor Boolean operation. At a certain point, at the 16th node, if I remember well, we will finally encounter our comparent. The 17th node, actually the 18th because we started from 0, is the I = 1. And this was a very, very stupid game, but I hope that it kind of like got into the mindset of, okay, I'm exploring my tree, and this will be like super, super annoying. And the way in which I iterate through it is kind of like different from the way in which we read our code. Maybe we read our code one line at a time. I read my code one line at a time, being a human being. That's what I do. So, having gone past through that, the next two super cool things that basically AST provides us are node visitors and node transformers. As you can understand, node visitor basically allows you to just do funny stuff when you just read your own abstract syntax tree. Node transformer basically allows you not only to just read the tree, but to return a modified version of your tree. Node transformer is the kind of like super evil thing that you use when you want to automatically transform your code. So just to like give you some kind of like guide on how this works, node visitor is basically just this class, this abstract class that needs to be kind of like it needs to be a base class. So you need to write a class that inherits from it, and basically it gives you a method which is visit. You can pass it in input tree, or maybe like just a subnode of your tree or whatever, and it will just perform activities every time it encounters a node for which you defined a function which is visit underscore and the name of the node. That's why the name of the nodes were super, super important, because basically the APIs of AST require you to know the name of the node, and they perform specific activities on specific types. So in this case, what are we doing? We just developed a stupid node visitor in which basically says, okay, every time you encounter a function def, it has the signature, of course, you need to pass it to itself and the node itself, but the node will be of type function def. Do something with this function definition. In this case, okay, if it has a return annotation, this will just print the name of the function and the ID, basically. Also, a very, very important thing, you actually always need to invoke generic visit if you want the sub-nodes of the node you are actually handling to be also explored by node visitor. Let's say in this case that you want to track nested function definition, like you define a function, then you define a function inside the function. If you don't write self-generic visit, you are going to miss all of the children function, all of the sub-functions that are nested inside the first function that gets encountered. This is just to say that thing to you. And once we saw node visitor, the next cool thing is node transformer. Node transformer basically allows you to take your abstract syntax tree, and every time you define one of its callbacks, you can basically tell him the node that it needs to return, which can be the same node, but it can also be the node modified or a completely different node. In this case, we have this node transformer. We'll just okay, say visit tree and then reassign the tree. In this case, every time we go through a list comprehension, of course we do the self-generic visit in order to take like nested list comprehensions, but basically we are returning a set comprehension instead of the list comprehension with the same internal attributes of the node. So this is like the same list comprehension, the same thing, but this time it is a set comprehension. Why are we interested in doing this? Well, I have no idea, but I mean, it could have been fun. Other helpers before the demo, you can have like a lot of like other support functionalities inside AST. If you're interested in taking a look at the source code of a node, there is a function for it, get search segment. There is a get docstring, which basically allows you only for, if I remember well, classes definition, function definitions, and hopefully I also think assign function definitions. It will give you the docstring of your node. It is easy to access it. You can iterate through the child node, through the children of a specific node. You can print the AST, as I was showing you before, and there is also super cool unparse. Unparse allows you to take an abstract syntax tree, you modified it, you did whatever you wanted to do, and you can regenerate the code. Sometimes this is actually easy. I mean, sometimes when I want to generate some Python code, actually like string formatting has some limits, because maybe it happens that they need to generate like code section 1 and that code section 2. Code section 2 depends still on code section 1, so I don't want to just reparse it again. You can basically just generate your Python code by building an abstract syntax tree and then just feed it into unparse. You can do that. So, arriving at this point, I hope that you are all like ready and everything. There is a demo. So, I hope that you can basically just see the code, that the character size is enough. I thought about something dumb. Let's just take a code base. In this case, I just cloned Pydantic. I don't know which version of Pydantic. I did it some time ago. And my idea was like, okay, let's iterate through all of the files of Pydantic and collect some stupid data about Pydantic, about its stuff. So for example, just to showcase you the code, the main loop, we are just iterating throughout all the files from our root folder. We then take the code. We then parse the code, so that we obtain for every file its module. And then, well, I just wanted my node visitor to just always have an updated file path and the updated code so that I can play with that while I go through the nodes. And then, okay, I just visit it. From there, well, I defined a node visitor because I wanted to collect some stupid data out of Pydantic. And basically, okay, I initialize it with some stuff that I'm going to fill in. And I have the set file method. But just the first thing that I wanted to do was like, okay, let's just scrape some function data. And basically, okay, if I want to do this, not visitor, I just overload function def, visit function def, And okay, I can just create a set of function names, I can get the docstring, and then since I wanted to build a data frame, I can basically just build a list of dictionaries, which will be then converted inside the data frame to just have the function name, line number, the number of lines, the number of characters. I can easily take the number of characters by taking the length of the search segment, because there is an AST helper to get the search segment, and I can basically just then plot some stuff out of that. Which, if we run it, I just set a lot of other things to false, because I didn't want to have any other prints. Just to give you an idea, if we want to take some data out of the whole code base, I then just need to run this. And once this thing basically just unrolls and goes through like all the files and all the functions inside Pydantic, I want to say, okay, let's have a scatter plot with, on the x-axis, I hope that you get to read this, the number of code lines, and on the y-axis, the number of characters. I was interested, like, are they correlated? And then I have to say, yes, they are correlated. Nice funny thing that you can do with not much effort, honestly. You can just build your own distribution plot of the number of code lines inside every function of Pydantic. This is kind of like doable. The next thing that I wanted to, that I was kind of like curious, it is a stupid question, but I was curious. Does Pydantic use data class? Is there anybody who is here is interested in like knowing if Pydantic, which basically gives another, just kind of like say an alternative to data class, inside Pydantic are data classes used? Okay, let's take a look at it. We just have, my idea was like, okay, let's visit all the class definitions. And the first part is to just take a look at the callables. We are not interested in this, not now. But then if we want to check where are all the data class, okay, I need to basically take a look at the decorator list of my class. Then I just take the ones which are not called, just names. And I just say, okay, if inside the decorator ID, inside the node ID of my data class, of the data class decorator, of my decorator, there is the data class string, okay, let's just print it. And if we run it, we'll basically see that there are some cases inside Pydantic. I will just zoom in a moment, where the data class is actually used. There are many, many more, honestly, but there are cases in which data class is actually just, how to say, just invoked through a call and not just through a name. So I have at this point, there are worlds beyond, like I just kind of like dipped my toes inside AST, but you can do a lot of stuff. AST offers you to compile the bytecode, and there is an ecosystem built around Dust. Finally, some personal opinion from my side. I have to say, it is rare, unless you really have a personal project in which you really, really need to just do a lot of parsing, it is rarely useful in my life. But when it is a game changer. Like, it makes you feel like a 10x developer, because you can do like pretty much crazy, crazy stuff. Also at your job, things like, oh my God, we need this type of thing, it will take 1 month. No, 2 days, AST. So if you think it could serve it to you, I mean, you saw it's in the standard, it's there, 10 characters, you can import it, and it's useful. Links to the resources, there is, okay, the official docs. Green Tree Snakes is kind of like the unofficial docs, and it's super, super useful. There is awesome Python AST, and the memes at the beginning were from Programmers Are Also Human. I love the channel on YouTube. And, well, thank you for the attention.
Thank you, Domenico. Thank you. So there are a couple of questions. You can still add some more questions. The first question is, can you access the parent node in the AST visitor?
The parent node?
Parent.
The parent node in the AST visitor? I fear not. In my humble and super limited knowledge, I still didn't find a way to do that, honestly, because I never ever saw it among the attributes. That's a kind of like limitation, but that also is also like up to my super limited knowledge. I put it in advance, I just have 2 years. So maybe if there is kind of like a guru, he will tell you, oh, okay, there is a hidden way. I just never found it in 2 years that I'm using it.
So this was a question by Florian, and if you want to raise your hand while I say the question so that the speaker can look at you, you are welcome to do so. If you do not want to, you can also be anonymous. There is another question by W3R. Is the AST parse function specific for the Python language, or is it possible to use it with other languages, or even custom structures?
from what I hear, it only works on the Python language, because basically this language it's not like a parsing library. This is just CPython internals. This is CPython's internals that get exposed. But the abstract syntax tree is not it's not something only with Python. I mean, it's a theoretical programming concept. So there are abstract syntax tree libraries also for other programming languages. You just have to go take a look at that implementation and take a look at the library. I even have a doubt that PyPy has its own AST, because if you go and take a look, for example, just PyPy, which is another Python implementation, has its own abstract syntax tree. I played with it for one night just to play, and it looks like it's almost the same if you take a look at the beginning, but it's, but how to say, this is not a parsing library. This is an internal thing to make Python work. It just gets exposed.
Okay. Then I have another question. So you use the AST to analyze code and to extract statistics. Have you ever used it to generate code on the fly at runtime and run that code?
No, I never did that kind of heavy stuff. It's the next step. Like probably in this year I will try to do this. It's the next step.
Okay. We have some time if you want to raise your hand and do a question the old style.
Or we can take a look at other like stupid things that could have been done with the EST. I don't know if
you want to have another minute for another demo.
But I will use it. I will waste your life for 1 minute for an additional minute. Like, come on, if we are at. Yeah, come on, let's do. We are all here to Pythonize. So I think one thing that makes like kind of like this thing useful is actually like okay, because I mean data class you could have done it with a text search, and that's the okay. But let's say that you are interested in saying okay, what are all the callables inside Pydantic? Bang, and you have to do it by string manipulation. Bang, you can look at all the call patterns, and also let's say that, I mean, you have to take a look at everything that it's not inside a comment, but if you want to do that with EST, it's kind of like easy. You just take a look at all of the classes, you can iterate through all of its elements in the body. I didn't even wanted to use walk. Then, okay, if there is a function def, which is name is call, okay, then you know that you have a callable. That is just one stupid code example, but this is one of the situations in which, okay, having a parsed data structure is actually way more helpful than just performing just search on a string. So sometimes it's pretty like a 10x trick importing this library, in my humble opinion.
Okay. Thank you again, Domenico.
Thank you for the attention.